All right, so let's go ahead and get started. Today we are looking at the second method for uh, determining initial rates. It is called MOIR, our method of initial rates. So yesterday, yesterday we were doing it by looking at mechanisms, and essentially mechanisms are the individual steps that a chemical reaction undergoes to get to its finished product. So, if you're trying to produce a certain product and depending on what you start with, you're going to have to go through these steps or varying steps to get to your final product. Today is more of an algebra type thing. It is just manipulating the numbers that are given from experimentation. So what we were doing yesterday would be based off of theoretical information, what we have from tables and charts and all of that. Today is more experimental data. So, oh man, my battery's not, my battery's dead. All right, so today what we're dealing with is going to be more experimental data as far as this material. So let me put that right there. All right. So so yesterday we learned that undo undo pin guys. So yesterday we learned that that rate is defined as the change in the concentration of the reactant over the change in time. So typically, when we're doing MOIR, we are going to be looking at two or more experiments where we have rate data from two or more experiments that we can compare. Most of them that I've seen has been up to three experiments within the within the within the composition. So let's just go ahead and look at it. What you're going to be looking at is each experiment is going to have a concentration for each substance involved, and then it's going to have a rate for that. And then what you'll see is we manipulate the concentration of one or the other in every one of the experiments so that we can compare and solve for the order. So we're solving for that exponent on the outside of the concentration. So let's look at the first one. All right. So for method of initial rates, we need to go ahead. The first step that we're always going to do, and let me check my notes to make sure I say this correctly. First step is we always write the rate law, or the skeleton rate law. So step one, skeleton rate law. All right. So what would be, based off of this information, we have nitrogen dioxide plus fluorine yielding nitrogen, what is that, nitrous fluoride. What would be our skeleton rate law here? How does it start from yesterday? Okay, but it's going to concentration of NO2 to the Xth order times concentration of F2 to the Y order. So we are going to use this data to solve for X and Y. The next thing that we have to look at is we're going to pick two experiments, but we want to pick two experiments where, yes sir. This is our final 1. The x and the y come from the coefficients of the rate determining step. We don't have the rate determining step in this one. So we're using it from experimental data. So there's two, depending on what data they give you, you have to do it one of two ways. All right. So looking at this one, we want to pick two experiments, but we want to pick two experiments where the concentration of one of the substances is the same. So experimentally, when we look at F2 here, these numbers of 0.0318 and the number of 0.0315 experimentally is the same. There's not a significant enough difference there to make that different. So I'm going to pick experiments 1 and 2. All right, so my next step, I'm going to pick where one concentration is the same and one is different. All right, so I'm picking experiment 1 and 2. Now, for math's sake, you want to pick the one, you want to put the one that has the highest rate on top. So 1.90 times 10 to the third is a bigger number than 4.69. 10 to the negative third is a bigger number than 4.69 to the 10 to the negative fourth. So I'm going to put experiment 1.
Attention teachers and students. We're about to begin our lockdown and fire drills. Remember that during
5, 4, 3, 2. All right, getting back to this, we're basically what we're going to do is we're going to solve for x and y based off of the information that we have. So basically you're just going to plug in the numbers for the rate law based off of what you have. So for experiment 1, we're putting experiment 1 on top. Our rate is 1.9 times 10 to the negative third equals K times the concentration of NO2, so that's 0.0482 to the X times 0.0318. And this is molar too. All right. To the Y. Now, you're going to do the same thing with experiment 2 on the bottom. You're going to plug it in so your rate is 4.69 times 10 to the negative 4 equals K times 0.0120 molar to the X times 0.0315 molar to the Y. Yes? That's just letting you know that there's a left and a right side to the equation. All right, now, looking at this, there are things that can cancel. We are going to treat these two as the exact same number because it's only difference in, what would that be, the 100,000ths place or 10,000ths place. So that cancels, that cancels. What else can cancel? What's the same top and bottom? K. All right, we're solving for the x, so the exponent there is different, so we're not going to be able to cancel that. So now all you have to do is take 1.9 times 10 to the negative third, divide it by 4.69 times 10 to the negative fourth, and what do you get? Yes, you actually get a number. So 1.90 times 10 to the negative third divided by 4.69 times 10 to the negative fourth. It is a positive number. It is a whole number actually. 4.05. All right. Now, somebody do 0.482 divided by 0.120. All right. So we get 4.05 equals 4.02 to the x. So what would our exponent be? 1. X equals 1. All right. So that means that in our rate law, x is 1. So that one's going to be a first order. So this equation so we would make the statement that this is first order with respect to all right, so it's first order with respect to NO2, and now we need to go ahead and solve for our y. So how are we going to solve for our y? We use two different experiments. Yes. So let's go with a different color. All right. So can you see that the concentration of NO2 is the same for that one? So that means that NO2 is going to essentially cancel out on this one. All right. So we already have our x, so that's just going to let us solve for our y this time. So we are dealing with experiment 1 and 3. So we're going to put 3 on the top, experiment 1 on the bottom. Does everybody understand why I put 3 on the top? Just makes for cleaner math. The rate's larger for 3 than it is for 1. So this divided by this gave me 4.05. This divided by this gave me 4.02. All right? So, go ahead. Because experiment 3's rate is larger than experiment 1. Yeah, well, it just makes you don't have to. It's going to come out the same either way, but this makes for cleaner math. This gives us whole numbers rather than decimals. Is essentially what it is. I don't want to have small decimals. I'd rather a whole number. So I'm going to go ahead and put it on there. So I have 7.57 times 10 to the negative third equals K 0.0480 molar times 0.127 molar. And that's to the X, that's to the Y. Now, technically, I could go ahead, instead of putting X there, I can put 1 instead, because we know that's 1 already. That's just really up to you. And then on the bottom, it is 1.90 times 10 to the negative third equals K times 0.0482 molar to the 1. All right. So again, on this one, we're going to cancel out what remains the same, and then we need to do our solving. So 7.57 divided by 1.9, because they're both 10 to the third, so that kind of goes away. So we get 3.98. That's just it. All right, 3.98, and then we go 0.127 divided by is it 0.127? Yeah. 0.127 divided by 0.0318 gives us 3.99 to the Y. So Y equals 1 as well. So this is first order with respect to F2. All right. So now, if you flip over to the next page, they actually had this kind of broken down into some questions. All right. So we know the order for F2, and we know the order for NO2 now. And so this question says, determine the overall order of the reaction. Guys, how do you determine the overall order of the action? You add them up. So it was first order in regard to NO2. It was first order in regard to F2. So it's second order. So we would just say second order overall. And even though this is math that you could do in your head, show your work, because they give you credit for that. So it's just saying, so I said first order with respect to NO2. That means that because of the concentration of NO2, it is a first order, so it is a exponent of 1. You just say that, that's just a statement that you're going to say. Second order with respect to F2 or whatever. All right. We'll do one more that has that. All right, so write the specific rate law. Rate is equal to K times NO2 to the first order times F2 to the first order. Simple enough. Now comes for the part where this is just the kind of culminating question. And all right, so this last one asks us, determine the rate constant for the reaction and include units. Whenever you see one like this, always use experiment 1 data. I'll tell you this, the main reason why is when I do my calculations on the test, I'm going to use it off of experiment 1. It helps me read the numbers better. Also, for the rubrics that they give on AP exam, the rubric is based off of the first one if they do this type of question. So that way, if you use a different one, you're going to come up with the same answer, but say the person is grading it and they start reworking it with the experiment 2 and they make a mistake, they will mark off. And that's just how it goes. All right, so you pick one of the experiments, pick experiment 1. So we'll just plug in the data. 1.90 times 10 to the negative third equals K times 0.0480 molar. Oh, and this is molarity per second, or moles per liter seconds. Maybe it is. I'm not looking at it. Yeah, it is 482. Thank you. All right, to the first power, and then it is 0.0318 molar to the first order. And then we just solve for K. So what does K equal? That is what I got as well. All right. So, guys, so notice that it does ask for the units in this question. I wanted to show you how you get the units in this one. You could do the long method for just canceling out units. So you have molarity over seconds times molarity times molarity. So you could cancel it out, and essentially your units is 1 over S times M. Or I'm going to give you a shortcut for units on this. Now, rate doesn't just go, or the rate constant isn't just in molarity. It can also be in pressure. So do this with a grain of salt. It works the same for both of them. But the unit shortcut is always going to be 1 over time times molarity, and then the overall order minus 1. So if we would have looked at our last equation, our overall order was 2, right? So it's going to be 1 over time. Our time was in seconds times molarity, 2 minus 1, which gives us 1 over S to the M, right? So that's a shortcut to getting your units. And if it was in pressure rather than molarity, you would just replace it with whatever the pressure units are there. So like millimeters mercury or torr or atmosphere. Overall minus 1. Overall order minus 1. All right. Now, so that first one was using algebra. When you have numbers like the concentrations and the rates that we had on that last one, algebra is the best bet because you can't really necessarily just look at it and cancel things out. There is another way to do this that is just basically called the inspection method. So if we look at this next equation, you can do it by inspection, but when you do it by inspection, you have to make sure you explain your answer since you're not showing any work. So let's go ahead, consider the reaction in the following initial rate data for nitrogen monoxide plus hydrogen yielding nitrogen gas and water vapor, H2O. All right, so what's different about this data table since the last one? It's in pressure rather than concentration, but it works the same. All right. So one of the things that I will point out with pressure versus concentration. So when we write our rate law, when it's a pressure, we are not going to use brackets. We're going to use parentheses. So when it's a pressure, you use parentheses instead of brackets. No big deal. Some people will take off of that. So your rate is equal to K times NO to the X times H2 to the Y. That's our skeleton rate law. Now, so I'm going to look at experiments 1 and 2. I can cancel out my two pressures there because they are the same. So that leaves me with this to this. What is the difference from 150 to 300? 2. So that's a factor of 2 that it's going up by. What's the difference between 0.66 and 1.34? 2. All right. So 2 divided by 2 is what? 1. So this is first order with respect to which one? To H2. All right. Now, the only problem with this is that's not enough explanation to get full credit on it. You do need to explain. And this is the way I was taught to explain it. You basically make a statement as the pressure of NO held constant as the pressure of NO was held constant, the pressure of H2, what did the pressure of H2 do as the pressure of NO was held constant? Doubled. All right, and then we're still not finished, so doubling the H2 pressure caused the rate to do what? And there's your explanation. Personally, I prefer to do the algebra because I don't like to write. Yeah, the algebra is simpler to me, rather than having to justify all of that. All right, so now let's go ahead and look. So that's our order with respect to H2. Now we need to solve for pH. We need to solve for NO. So we're going to look for one that has H2 held constant. So we're going to look at 3 and 4. So we can cancel out the pressures of 3 and 4 because they were held we can cancel out the pressures for H2 because that was held constant. So what is the difference from here to here? All right, so it doubles. And then what's actually happening here? It is quadrupling. So what is our overall order? 2. So it is second order with respect to, what is that, NO? NO. Now, how would you make a what would you say is your justification statement for this one? As the pressure of, hold on, start with, as the pressure of H2 is held constant, the pressure of NO doubled. Doubling the pressure of NO caused the rate to quadruple, or caused the rate to increase 4 times. Something along that lines. All right. So, again, it's going to be hit and miss. Some people like the algebra method. Some people prefer inspection. I personally, if the numbers are clean, I'm going to do this. But I hate to write to do the justification. So I might still set it up in the equation and just do real quick math. But so you can either show your work for the justification or you can write this statement for your justification. It doesn't matter which route you choose. You just have to justify it. You have to explain it. All right. Now, going over to the rest of this material. All right. So what is the overall order of this reaction? It is going to be 1 plus 2, so it is, you add it. So it's 3. So this is a third order over all. All right, the specific rate equation. What exponent am I going to put on NO? 2. What exponent am I going to put on H2? 1. All right. So that's that. And then the last one is solving for K. So we just use the information from experiment 1. Experiment 1 data, which is our rate is 0.66. And on these, you need to make sure you include the units so that you can track the units and show the units and all. So it is millimeters mercury over seconds equals K times, and again, pay attention that you use parentheses rather than brackets. It's going to be 400 millimeters mercury NO2 raised to the first power times 150 Hg H2. Oh, I did it wrong. Yes, you're right. That one's to the second. because it's pressure. Yes. Um, some people, I'm not going to take off for that, but the people that are grading AP will because they're a-holes. Um, they're jerks. Somebody will take off because they can. Just like just like a lot of teachers will take off for sig figs because they can. I don't. I don't see the point. It's the right answer still. No, I don't feel like taking the time. It's more work on me. I'm lazy. All right. So solve for K. Now, you can also do your because that was the rate for experiment 1. All right, so I'm using my little shortcut. So my units are 1 over seconds, millimeters mercury times 3 minus 1, which is 2. So my unit is going to be 1 over seconds, mmHg to the second is my unit. And what number do we come up with? All right, so I put 2.8 times 10 to the negative 8. I got negative 5. I mean, I could be wrong. I could have copied it wrong when I did it. All right. So 2.8 times 10 to the negative 8, 1 over seconds, millimeters mercury to the second. All right, so any questions about this? Now, I am not going to work this one with you. I am not going to hold you responsible for this. This one is actually beyond the scope of what we would do. This is the one that I didn't try it. I'm not going to try it. I will tell you if you want to try it, start with experiments 1 and 2. And then the only other thing that I'll tell you is your orders that you're going to get, because there is an equilibrium reaction in this one. You will get first order for A. No, sorry, not first order for A. You'll get a half order for A, first order for B, and second order for C. Because it's an equilibrium reaction, you can actually get a half order. If I was doing this, I probably would have went with first order for A, second order for B, and fourth order for C. Yeah, but I would have probably lost points on that because my brain doesn't work the way this does. All right.